Scientific communities around the world have determined that the most important issue in the status quo is climate change due to excessive emissions, depleting the ozone layer. And I attempted to look forward to a world with little to no emissions. So I conducted research to develop a comprehensive molecular explanation behind nickel-palladium hydrogen sensors in order to stimulate the hydrogen-powered automobile market through a density functional theory approach. So essentially, hydrogen-powered vehicles are very unique and special in the fact that they have zero emissions that will harm the ozone layer, only water vapor, which is completely harmless. However, when hydrogen gas accumulates, it's an explosive hazard. So we need hydrogen sensors to sense this accumulation of gas. However, hydrogen sensors are either very, very expensive, and very effective, or not very expensive, but also not very effective. So I wanted to take qualities from both of these types of hydrogen sensors, merge them into one commercially feasible sensor that manufacturers can get their hands on easily, but that will also help sense these accumulations of hydrogen gas and make hydrogen-powered automobiles a more feasible solution for the average consumer. So all we really know about hydrogen sensors under the status quo is that the change in the substrate from the alpha phase to the beta phase, a more to a less conductive phase, accounts for hydrogen sensing. Most of our data behind hydrogen sensors has been experimental. So what I wanted to do is conduct a comprehensive molecular explanation behind the function of these hydrogen sensors in order to give experimental chemists the framework of what they need to work with to synthesize an ideal and optimized hydrogen sensor. So what I did was I analyzed factors such as the stability, the metallic properties, and I quantified the current exchange between the surrounding hydrogens and the hydrogen sensor to develop this explanation that the scientific community trying to synthesize hydrogen sensors needs. So I used density functional theory, specifically Purdue and Wang generalized gradient approximations, which deal specifically with absorption and adsorption energies. Since what I did was I modeled the absorption of hydrogen molecules or hydrogen atoms on the clusters. And what I found were that mixed 13 atom clusters with dissociated hydrogen on them were the most stable. So essentially, I found a lot of molecular data that will help experimental chemists synthesize the optimized hydrogen sensors so that the hydrogen-powered automobile will become feasible for our country and for our world.